Okay, so recall that if, let's say, P1, P2, Pn are fixed sets, and say that we have, of course you don't recall this because we didn't write anything like this, but I'm basically restating the principle of induction at the moment. We have, let's say, that this holds, and for any natural number n, whenever this formula holds, blah, 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 blah. If we have this, then for all n in n, this holds. Why is this the case? Because let's construct the set I, which consists of all natural numbers n such that phi of n, p1, p2, dot, 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 pn holds. Okay? Now, these two properties together imply that this set I is inductive. Okay? So, these guys simply imply that I is inductive. And the principle of induction says any inductive subset of natural numbers is the set of natural numbers. It's the whole thing. Okay? So this gives me a method to prove things about natural numbers. If I can show that some property, there might be some fixed parameters around, some property holds for 0, and whenever it holds for a natural number, it holds for the natural number. If I have such a property, then that property actually holds for all natural numbers. Okay, so we saw an example. Let me assign two exercises that are going to be used in the proof of one of the theorems today. Prove that for all natural numbers k and n, we have the following. If k is strictly less than s of n, which is, how did we define this? This simply means that k is a member of s of n. We have the following. Okay, so if k is strictly less than the successor of n, then k is either strictly less than n or it equals n. And prove that also. Prove that for all n, if n is different than 0, then there exists some natural number k such that n is the successor of k. Okay? So prove these two. How are you going to prove these? You're going to prove these by induction. Okay? Well, maybe I should rewrite this part. I don't want an if-then statement. I want this. If n equals 0, for all n, either n equals 0, or there exists such a number k such that n is the successor of that. It's the same thing. I just rewrote the if-then statement. So prove these two. How are you going to prove these? You're going to prove these by induction. I know that these seem so simple. At least this seems very simple. If k is strictly less than the successor of n, obviously it's either strictly less than n or it equals n, because this is supposed to be the successor, the next thing. But you should prove this by induction. And this says that any non-zero natural number is the successor of some other natural number. Okay? So prove these by induction. And that's an exercise. Now let's prove a very important theorem. Important as in, well, okay, all of you know that you might have learned in like 111 or 116 that every subset of natural numbers has a minimal element, right? which is the same thing as saying that natural numbers are well ordered by the usual ordering. Well, that's true. We use this a lot. This is why I said this is important. I'm not implying that this is difficult, but it's important. This is used a lot. It's the following fact. This set is well ordered, where, remember, we defined this relation by the membership relation. Now, because I'm using the symbol strictly less than, you're already thinking that this guy defines a strict linear order relation on the set of natural numbers, but that has to be proven. It's not obvious why this actually defines a linear order, okay? So let's prove this. How do you prove that? Let's first prove that, forget about well-orderedness. Let's first prove that this is actually a linear order. How do you prove such a thing? What do we need to prove? We need to prove that this is a partial order where every two elements are comparable. So how do you prove that something is a partial order? You show strict partial order. You show two things, that this is asymmetric and transitive. Remember, a strict partial order relation is a relation which is asymmetric and transitive. So let's prove that this is transitive. Okay? I want to show that this relation on natural numbers is transitive. What does that mean? I want to prove the following. If M is a member of N is a member of K, then M is a member of K. Like, if you look at the picture of natural numbers, that's obvious, but pictures are not proofs, as you know. So let's actually prove this. We prove this by induction. So one of the reasons I'm doing this proof in detail is it shows you have to prove things about natural numbers, okay? So let I be the following set. I'm taking the set of all natural numbers Z such that I have the following implication. Okay? You have a question? No. Okay. Now, why am I doing this? What do I want to prove? I want to prove that this relation is transitive. What does it mean for this what does it mean that this relation is transitive? Like, how do you state it? It means the following. For all x, y, z, this happens, right? So I want to prove that this is true for all x, y, and z. How am I going to prove that? This is a statement about natural numbers, so my first instinct is to go with induction. So what I do is, I take the set of all z satisfying this formula. I take the set of all z such that for all x, y, this is true. If we can show that I is all of n, then that would mean that for all natural numbers x, y, z, this happens. If I can show that all natural numbers are in this, then in that case, I will have shown that for all x, y, z in natural numbers, this happens, which is the same thing as saying this is transitive, okay? Then we would have that for all x, y, z, and n, we have the following implication. This is exactly what it means for strict less than to be transitive. Okay. How do you show that a subset of natural numbers is the whole thing? There are many ways, but what should we do? It's over there. We use induction. We proceed by induction. Now, 0 is an I clearly. I'm going to say clearly, and I'm going to explain why it's clear. I claim that whenever you plug in z equals 0, this is automatically satisfied. Why? Because this statement becomes vacuously true. If you plug in 0 here, then this if-then statement is true, because what is this? Y is strict less than 0. This is the same thing as y is a member of 0. 0 is the empty set. there is no y which is a member of the empty set. So this is automatically false. When the premise of an if-then statement is false, the statement is true. So this guy becomes vacuously true for z equals empty set, okay? Maybe I should emphasize that this is the empty set. So this is automatically true. Now let m be a natural number such that n is a member of I, okay? Now we wish to prove that S of n is an I. What does this mean? This means the following. For all natural numbers xy, this and this implies x is strictly less than successor of n. Okay, so we want to prove this statement. So let xy be natural numbers and assume that x is strictly less than y and y is strictly less than S of n. So assume this. We want to prove this. Okay, how is that going to happen? By exercise, we have, this is why you should do the exercise. By the second exercise, this implies the following. Y strictly less than successor of n is the same thing as y strictly less than n or y equals n, okay? Now, if y is strictly less than n, then by induction assumption, by the fact that n is an I, you see, this happens and one of these happen. One of these happens. Let's assume that this one happens. X is in y, y is in n. But n is in I, so it satisfies this. So just by using this fact, I'm using the induction assumption in a way. Well, not in a way, I'm literally using the induction assumption. I'm using the fact that n is in I. X is in y is in n. We have x is in n. If y is n, then x in y, you see I keep saying in y because I want you to remember how this is defined. X is strictly less than y if x is in y for natural numbers. Then this gives x strictly less than n. You see, in any case, I got x strictly less than n. Thus, we have x strictly less than n. So, sorry. So something is off here, obviously. If y is in n, no, something is off here. What have I assumed? Yes, this is wrong. Okay, this is fine. By exercise, we have this and this. If this happens, then x is less than y is less than n. By induction assumption, x is less than n. That's fine. If y is n, then I have, yes, x in n, and we have x in S of n. Why? Because this is defined to be the union of these guys. If x is in n, then this is automatically satisfied. So x is less than successor of n, okay? Now, we assumed this, and we got that. So we proved this, and this is true for all xy, so we proved this. So successor of n is an I. Therefore, I is inductive, and I equals all of n by the principle of induction. Okay? Now, we prove that this relation is transitive. Let's prove that it is asymmetric. Now, I'm going to take some shortcuts here. That this relation is symmetric can be proven by induction. However, I'm not going to do that. I'm going to prove it by axiom of foundation. Let x, y be natural numbers such that x is in y. Then it follows from the axiom of foundation that now if x is in y, y is not an x, right? And if x is in y, x cannot be y because naught is a member of itself. So both of these come from the axiom of foundation. Okay? I only need this, but that's fine. So this comes from axiom of foundation. Well, if y is not an x, then y is not strictly less than x because this is how we define being less than. Now, I used axiom of foundation. In truth, you do not need axiom of foundation. You can prove that this is asymmetric without axiom of foundation. But then you have to do an induction argument, and induction takes, you see, 8 lines. So I don't want to do that. So we now have a strict partial order relation, transitive asymmetric. Let's prove that any two elements of N are comparable with respect to this relation. Okay. Now I have to do induction again, okay? We're going to do a similar thing. Let N be the set of natural numbers such that for all M, okay. What do I want to prove? Any two elements are comparable with respect to this strict partial order relation. What does that mean? For all M and for all N in natural numbers, either M equals N, M is less than N, or N is less than M. Maybe I've said it wrong. I don't care. You know what I mean. So for all M and N, either this happens, or this happens, or this happens. So I'm going to say, okay, forget about N. Let me write down this property. I take the set of all natural numbers satisfying this property to be I. We proceed by induction. Now let's prove that 0 is an I. Why is this true? Remember, we proved last time that 0 is less than or equal to all the elements of natural numbers. We proved this, right? It was the first induction we did. So this part by itself requires an induction, which we did last time. Now, let M be a natural number and assume that this N satisfies the formula that I want to prove for all natural numbers. Let's say, assume that it is in N. Let me also clear this board. Okay, so we want to show the successor of N is an I, okay? So we want to show that the success, when you plug the successor of n here, this is satisfied. How do you show that? Let m be some natural number. Okay? Then, take any natural number. What do we know? Let's try to write down what we know. Because you can't prove something from nothing, you have to know something. And over here, we assumed something, we know something. N is an I. So let's use that fact. Since n is an I, this happens, or this happens, or this happens. Now, n is a member of successor of n. And it's also a subset of this. We have that because I already have n here. So n is a subset of S of n, and it's already a member of that. Why did I write this down? Since this happens, if we're in this case or in this case, then we have that n is a member of, m is a member of S of n. You see, if m equals n, then m is a member of S of n. That's fine. If m is a member of n, then it's a member of S of n. So this happens in both of these cases. So m is less than the successor of n, okay? So if we are in the first two cases, it's fine. Now let's take care of this other case. Thus, it suffices to show that if we are in this third case, which we have not covered, then this happens. Okay? What am I trying to prove? I'm trying to prove that S of n is an I. I want to prove that when I take some natural number m, this and this guy are comparable. If I'm in the first two cases, then they are comparable. This guy is strictly less than this. What I want to prove is if I'm in the third case, then they're still comparable, meaning that either this happens or this happens, okay? If I can show that, then if I can show this, what will have I shown at the end? I will have shown the following. In this case, these are comparable. In this case, these are comparable. In this case, they're still comparable. So S of n is comparable with m, meaning that S of n is an I. And by induction, I would be the whole thing. So this will be true for all n. And now, we're going to do another induction within this induction. So we're doing kind of a double induction. Well, double induction is a specific meaning, so let's forget that. We're doing an induction within an induction, okay? So we want to show this. We want to show this statement. Now we're going to prove this statement by another induction argument. We prove this by another induction argument. Now, I'm going to change my letters so that you don't get confused. Let J be the following subset. J in n for all k in n, k strictly less than j implies S of k is less than or equal to j. When I write less than or equal to, you know what it means. This means that either this is strictly less than j or they are equal. So the same thing as writing successor of n. This is the same thing as writing successor of n is less than or equal to m. So we want to prove this. Now, let's show that 0 is in J. Again, I'm going to write clearly here, because if you plug in 0 for J, this means membership. So K is in the empty set. This is never true. Therefore, you have an if-then statement whose premise is always false, which means that this is always true. So this is a vacuous truth. So this just happens. Okay? Now, let J be a natural number from big J. So we have J and J. What do we want to prove? We wish to prove S of J is in big J. That is, for all K in N, K is strictly less than S of J implies S of K is less than or equal to S of J. Okay? We want to prove this. How do you prove such a statement? How do you prove a universal statement, which is of the form for all something blah blah happens? You take such a guy and you try to prove the rest. Any questions? No. Now, let K be a natural number and assume that this premise is satisfied. Then K is a member of the successor of J, which is J union the singleton containing J. Hence, there are two things that can happen. Either K is in J, or K equals J. Okay? Now, case 1, let's say that we're in this case. K is in J. Then, now I'm going to use the induction assumption. K is in J implies that successor of K is less than or equal to J. Successor of K is less than or equal to J. What does that mean? It means that it's either strictly less than J or it equals J. In both of these cases, we have that S of K is strictly less than or equal to S of J. Actually, we have strictly less than. Why? Let's say that we're in this happened. If this happens, J is strictly less than S of J, right? So I'm using the transitivity which I proved. This is less than this. Like S of K is less than J. J is less than S of J. By transitivity, S of J is strictly less than this. Let's say we are in this case. Well, J is a member of S of J. Therefore, J is a member of S of J. So I have that. So if we're in this case, then that's fine. If we are in the second case, K equals J, then K equals J, good. Then S of K equals S of J, clearly. Therefore, this still holds. Okay? So in both cases, I have S of K less than or equal to S of J. In this case, we have something stronger, but I can just put this. That's fine. Okay. So what have we proven? We have proven that whenever J is in J, S of J is in J. Thus, let's create a little box here. Thus, by induction, J is all of N. So this is true for all J, which means that I have just proven this statement in the orange box. But this was sufficient to prove the previous, this was sufficient to prove complete the previous induction. So the whole proof is now done. This finishes the proof that J is all of n. That J is all of n finishes the proof that I is all of n. Okay? So we're doing a double induction. Okay? Induction within an induction. Questions about this? Now, the reason I'm just writing all these things in detail is I want you to actually get used to doing all these arguments, because after some time, I'm not just gonna not do this. I'm just gonna say, hey, you can prove this by induction on your own, okay? So you should know how to write these out, how to write these down. Now, we proved that, okay, we already proved, let's see, we had that this was a strict partial order. Now we have that it's a strict linear order. Now let's prove that it's a strict well order. In the notes, I left this part as an exercise. In class, I'm just going to do it. Now let's say that this is a well order. Okay, so we already proved strict well order. Strict well order relation. We already proved this is a strict linear order, okay? Which took some time. Now, how do you show that a strict linear order is a strict well order? You show that any non-empty subset has a minimal element. So, let S be a non-empty subset. Of n. Now, that such a subset has a minimal element can be proven by induction. Indeed, if you like, we don't have an official textbook, but these notes I prepared, I extracted some parts, maybe half of the whole thing, from Yek's book, Introduction to Set Theory. If you grab that book, which is in your syllabus, you can find the ISBN number. You can see that this is proved by induction. Because at that point, he doesn't introduce the axiom of foundation, but I introduced the axiom of foundation, so I'm going to take a shortcut and prove this without induction by axiom of foundation. By the axiom of foundation, there exists some set S. I have a non-empty set, which means that there is an element of it which is disjoint from it. Such that this is empty. If S were not minimal, I'm going to write less than minimal. Meaning, what I mean is, this means minimal with respect to this relation. Okay? If this were not minimal with respect to this relation, then there would be T in S such that T in big S such that T is strictly less than little s. What does this mean? But this implies that T is a member of big S, T is a member of small s. So it's in the intersection, which is a contradiction. So every non-empty subset of natural numbers has a minimal element with respect to the membership relation, okay? With respect to the strict less than relation. As I said, you can prove this by induction without using the axiom of foundation, but this is like way shorter, okay? Now, we have finished proving that the natural numbers, together with the membership relation, together with the strictly less than relation that I introduced. Why do I keep saying strictly less than? Like when I say less than, it's automatically understood it's strict, right? Because otherwise I would have said less than or equal to, so I'm just keep saying less than. The set of natural numbers together with the relation less than forms a well-ordered set, okay? We have finished proving this. Now, let me assign a couple exercises. I should have erased that board, but whatever. And then I'm going to introduce some definitions. Some definitions I promised earlier. For example, we talked about sequences and n-fold Cartesian products. Maybe I may have mentioned these. Maybe I have not, I don't remember. But even if I did, at that point, we had not constructed the set of natural numbers. Now that we have those, we can precisely define what's the sequence of length n, what's an n-fold Cartesian product. So we're going to define these now, but an exercise before that. This is easy to solve, terrible to write down. Like if you want to write down in complete detail, show that now. Let's take any natural number. This is a set. This is a relation on this set. This is the membership relation on n. Remember what this was. This was the set of all ordered pairs such that A is in B. Now, prove that this is a well-ordered set. For all natural numbers. Okay, how do you prove something like this? Something happens for all natural numbers. You prove it by induction. Okay? For 0, you have the empty relation, empty set. It's a well-ordered set. That's fine. Now do the inductive part. As I said, it's conceptually easy. It's tedious to write down, but this is important. The reason I'm saying this is important is like a set well-ordered by the membership relation on this set. This is going to be very important. We're going to define ordinal numbers to be sets alphas such that this is a well-ordered set and alpha is transitive, okay? So such sets where the sets which are well-ordered by their membership relation, they're important. And I keep saying well-ordered strictly. This is a strict ordering. Strictly well-ordered, okay? Yes?
How is it any different from the last relationship?
It's the same. It's the same. The only thing is, like, if I write this, I define this on all of n, right? Like, I'm restricting that. Maybe I can do it like this. I'm restricting this relation to n, okay? I'm just giving it a different name. It's the same thing. Indeed, you can deduce this from one of the exercises. Remember, I told you to prove that if you have a well-ordered set, any subset is well-ordered with the restricted relation. We just proved that all of natural numbers is well-ordered with the less e with respect to membership. This is a subset of natural numbers, and this is the restriction of the membership relation on all of it. So this is going to follow if you use the previous theorem. Otherwise, you have to do an induction argument. Anyway, definition. Now, at this point, we have natural numbers. Okay, we constructed natural numbers. We've seen that they're well ordered by the membership relation. Now, let's make some definitions which we use in mathematical practice, like sequences of length and n-fold Cartesian product. Let's define these using natural numbers. Let n be a natural number and x be a set. A sequence over x of length n is a function f from n to x. Okay? It's any function from a natural number to some set, it's a sequence. How? Like, we have an intuitive understanding of sequences, so let's understand how we identify these with the intuitive sequences we had in mind. This is supposed to represent the following sequence: f of 0, f of 1, f of 2, This goes up to f of n minus 1. So this is supposed to represent this sequence, okay? At 0, it takes the value f of 0. At 1, it takes the value f of 1. At 2, it takes this value, and so on. So this is a sequence of length n. Okay? So sequences over a set of some finite length is represented by such a function. Now, let me erase this. A sequence over X with index set. When people, like in calculus and other analysis courses, when people talk about just sequences without specifying the index set, they usually mean that the index set is natural numbers, okay? And such a sequence is simply a function from natural numbers to x, okay? So this represents the sequence f of 0, f of 1, f of 2, dot. It maps 0 to some member of x, it maps 1 to some member of x, and so on. This is a sequence. Okay, so that's that. And let's define n-fold Cartesian products. There are a couple ways to do this, defining n-fold Cartesian products. All of them turn out to be equivalent in a sense. I'll explain what that means. Now, let's say that I have sets A, B, C. I want to define A cross B cross C. How can I do that? One solution is the following. I can define this Cartesian product, and this is a set, take the Cartesian product again. And if I have another set, take the Cartesian product again. This is one way to define n-fold Cartesian products. You just take the Cartesian product of n many sets just by taking the Cartesian product 2 by 2 and iterating this. This is one way. Here's another way. Let n be a natural number, and let's make this non-zero to avoid stupidities. And we have n sets. Let this be an index system of sets. We define the n-fold Cartesian product of A0, A1, at the dot am minus 1 to be so this is the notation we use, and here's how it's defined. You take the product of this index system of sets. We did this, right? Taking the product of an index system of sets. Let me rewrite this in several different notations, several actually, 2. Okay, so we define n-fold Cartesian products using the definition of product of an arbitrary index system of sets. Okay? What else? What else do I want to talk about? Oh. Let's talk about binary functions, ternary functions, and so on. In general, n-ary functions. Let x be a set, and let m be a natural number. An n-ary operation on the set X is, and let's also define n-ary relations, okay, is a function from x to the power n to n. And an n-ary relation is, it's simply a relation. It's simply a subset of this. Now, I use this notation, x to the power n. What does this mean? Over here, if all sets AI are the same set, if these are all x, then the common notation is to write x to the power n. Okay? If you have n many x's, if you take their Cartesian product, n-fold Cartesian product, well, this is the notation that you should use. Anyway, so an n-array operation on a set is simply a function from n-fold Cartesian product to the set. An n-array relation is a subset of the n-array Cartesian product. Okay, so what we learned, like we learned about binary, we learned about relations, but for us relations were like binary relations. They were subsets of x cross x. I can generalize to n-array relations. Okay. If n is 2, your functions are called binary functions. If n is 3, they're called ternary functions. If n is 4, it's called quad something functions. They have names, but I don't care about those names. Now, next lecture, next hour, in 10 minutes, we're going to prove the recursion theorem. Why are we doing this? Okay, we have constructed the natural numbers. We put a relation, less than relation on it. Together with that, it forms natural numbers form a well-ordered set. So we have the order structure on natural numbers now. What else do we need if we are to play with natural numbers? We need arithmetic operations, addition, multiplication, and so on. Now, those are usually defined recursively, meaning that in order to add 2 to 5, you should first know how to add 2 to 4. And then you take the successor of the result of 2 plus 4 to get 2 plus 5. And similarly for multiplication and exponentiation and so on, we can come up with recursive definitions. But I can write down any definition. I can just define flying elephants with magic wands. Just because I can define something doesn't mean that they actually exist. So in order for those recursive definitions to make sense, I have to actually show that those recursive definitions actually correspond to sets. Like there are sets satisfying those recursive definitions. And that's usually done by something called the recursion theorem. Next lecture, we're going to prove that, okay, in 10 minutes. So be back here at 12:46.